In the desperate summer of 1940, Britain stood alone against Nazi Germany. The Battle of Britain raged in the skies above England, and RAF pilots were dying at an alarming rate. But they weren't just being outgunned. They were being beaten by physics itself. Every time a Spitfire or Hurricane dove to pursue a German Bf-109, its Rolls-Royce Merlin engine would cough, sputter, and die. The Germans could dive away with impunity, knowing the British fighters couldn't follow. Pilots watched helplessly as enemy aircraft escaped, only to return and kill again another day. The RAF estimated they were losing engagements they should have won, and with every lost dogfight, Britain crept closer to invasion. The problem had stumped the best aeronautical engineers in Britain. Rolls-Royce had thrown their finest minds at it. The Air Ministry was growing desperate. Britain needed a miracle, and it needed it fast. But the solution wouldn't come from a laboratory full of male engineers in suits. It would come from a woman on a motorcycle, carrying a metal washer that cost about 50 cents to produce. Her name was Beatrice Schilling, though everyone called her Tilly. She was a brilliant engineer in a world that didn't want women engineers. She raced motorcycles at 100 miles per hour in her spare time. And she was about to save thousands of lives with one of the most elegant engineering solutions in history. This is the story of how a simple metal disc, smaller than a coin, changed the course of the Second World War. To understand Beatrice Schilling's genius, we must first understand the problem that was killing RAF pilots. The Supermarine Spitfire and Hawker Hurricane were magnificent aircraft. Graceful, fast, and maneuverable, they were the pride of British engineering. At their heart was the Rolls-Royce Merlin engine, a masterpiece of mechanical design that produced over 1,000 horsepower. But both aircraft had a fatal flaw, and German pilots had learned to exploit it ruthlessly. The Messerschmitt Bf-109, Germany's premier fighter, used direct fuel injection. This meant fuel was sprayed directly into the engine's cylinders under pressure, regardless of the aircraft's attitude. Whether flying level, climbing, or diving, the fuel supply remained constant. But British fighters used a float carburetor, a design that had worked perfectly well for decades in conventional aircraft. The carburetor used a simple float mechanism, much like the one in a toilet tank, to maintain the correct fuel level. Gravity and atmospheric pressure did the rest, mixing fuel with air in the right proportions to feed the engine. This design worked beautifully under normal flight conditions. But combat was anything but normal. When a Spitfire pushed into a steep dive or performed negative G maneuvers, the laws of physics intervened with deadly consequences. The float in the carburetor would rise suddenly, shutting off the fuel supply. Simultaneously, the fuel that was in the carburetor would surge forward, flooding the engine. The result was catastrophic. The engine would either cut out completely or bog down so severely that the aircraft lost power at the worst possible moment. For pilots, the experience was terrifying. You're chasing a Bf-109, lining up your shot, when suddenly you have to push the stick forward to follow him into a dive. Instantly your engine dies. Your propeller windmills uselessly. Your aircraft, moments ago a nimble predator, becomes a falling brick. The German pilot, whose fuel injection system doesn't care about gravity, powers away while you frantically try to restore your engine. You have to roll the aircraft to restore positive G-forces, letting the fuel settle back into the carburetor. Only then, precious seconds later, does your engine cough back to life. By that time, your target has escaped, and you may have become the target yourself. RAF squadron commanders were filing report after report about this phenomenon. Pilots were developing elaborate workarounds. Some tried to half-roll and pull rather than push into a dive, maintaining positive G-forces throughout the maneuver. But this was slower, required more altitude, and in the heat of combat, wasn't always possible. Other pilots learned to anticipate the cutout and roll immediately, but this meant giving up the pursuit just when they had the advantage. Some of the more reckless pilots would simply push through the dead engine, diving without power and hoping to restart lower down. This often worked, but it also got pilots killed. The problem wasn't just academic. Combat reports showed that British fighters were losing engagements they should have won. German pilots were using what they called the cut and run tactic, diving away whenever a Spitfire or Hurricane got on their tail. The statistics were grim. Fighter Command estimated that this single technical problem was reducing combat effectiveness by as much as 30%. In an air campaign where Britain was already outnumbered, where every pilot and every aircraft was precious, this was potentially catastrophic. The psychological effect was perhaps even worse. RAF pilots were among the bravest young men Britain had ever produced. They flew multiple missions a day, faced overwhelming odds, and watched their friends die regularly. But they had faith in their aircraft. The Spitfire, in particular, was more than a machine to them. It was a symbol, a thoroughbred, the finest fighter in the world. To discover that this magnificent aircraft had such a fundamental flaw, one that could get you killed through no fault of your own, was deeply demoralizing. Pilots began to lose confidence, to second-guess themselves in combat. Some started avoiding negative G maneuvers entirely, which meant giving up tactical advantages. By early 1941, the problem had become critical. The Battle of Britain had been won narrowly, but the air war continued. RAF fighters were flying sweeps over France, escorting bombers, and defending against ongoing raids. The Luftwaffe remained a formidable opponent, and the Bf 109 continued to exploit the carburetor issue. Every day, pilots died or failed to return because of an engineering problem that everyone knew existed but nobody could solve. The pressure on the Royal Aircraft Establishment and Rolls-Royce was immense. Britain needed a solution, and it needed one immediately. Beatrice Shilling was not supposed to be an engineer. Born in 1909 in Hampshire, she grew up in an era when women were expected to become teachers, nurses, or housewives. Engineering was a man's profession, and the idea of a woman working with engines, mathematics, and machinery was considered somewhere between eccentric and scandalous. But Tilly Shilling, as she preferred to be called, never cared much for what was expected of her. From an early age, she was fascinated by how things worked. While other girls played with dolls, Tilly took apart clocks and mechanical toys, studying their inner workings. Her parents, remarkably progressive for their time, encouraged her curiosity rather than suppressing it. Her father, a middle-class professional, recognized his daughter's exceptional intelligence and supported her education. This was unusual. Most parents, even supportive ones, would have steered a bright daughter toward a teaching certificate or perhaps nursing. But the Shillings believed their daughter could do anything she set her mind to. Tilly excelled in mathematics and science at school, subjects that were considered particularly unsuitable for girls. Teachers didn't know quite what to make of her. She was polite and well-behaved, but she asked questions that challenged conventional wisdom and showed a grasp of technical subjects that many of her male classmates couldn't match. When it came time for university, Tilly applied to study electrical engineering at the University of Manchester. The faculty was skeptical. Some openly questioned whether a woman had the mental capacity for such demanding work. They let her in, perhaps assuming she would fail and prove their prejudices correct. She didn't fail. Tilly graduated with first-class honors in 1932, one of only a handful of women in Britain with an engineering degree. But having the degree didn't mean employers wanted to hire her. Company after company rejected her applications. Engineering firms told her, sometimes politely and sometimes not, that they didn't employ women in technical roles. It didn't matter that her qualifications were impeccable. It didn't matter that she understood thermodynamics, fluid mechanics, and electrical systems better than most male graduates. She was a woman, and that was that. While searching for work in her chosen field, Tilly discovered motorcycles. She bought an old bike, took it apart, rebuilt it, and then started racing it. This wasn't ladylike hobby riding. Tilly competed in real races against men, pushing her motorcycle to speeds over 100 miles per hour. She was good at it, too, winning trophies and earning respect in the motorcycle racing community. The men she raced against quickly learned that the woman in leathers on the powerful bike wasn't a novelty. She was a serious competitor who understood machines at a fundamental level and wasn't afraid of speed or danger. Finally, in 1936, Tilly found an employer willing to take a chance on her. The Royal Aircraft Establishment at Farnborough, the government research center responsible for developing and testing military aircraft, hired her as a technical officer. Even there, she faced skepticism and condescension. Some of her male colleagues assumed she was a secretary or assistant. Others made jokes about women and engineering. But Tilly had faced prejudice all her life, and she had learned to let her work speak for itself. She was assigned to work on engines, specifically carburetors. It was detailed, painstaking work that required both theoretical knowledge and practical intuition. Tilly thrived. She understood not just how carburetors were supposed to work according to textbooks, but how they actually behaved under real-world conditions. She would test engines for hours, measuring fuel flow, air mixture, and power output under various conditions. While other engineers relied on calculations and theoretical models, Tilly combined those with hands-on testing and observation. Her background in motorcycles, where she had tuned and adjusted carburetors herself, gave her insights that pure academics lacked. When war broke out in 1939, everything changed. The Royal Aircraft Establishment became one of the most critical facilities in Britain. Every aspect of aircraft performance mattered. Enemy aircraft were being shot down and examined. RAF pilots were debriefed after every combat mission. Engineers were working around the clock to give British pilots any advantage they could find. And increasingly, reports were coming in about the carburetor problem. Pilots were dying because of negative G cutouts. Fighter Command needed a solution. Tilly Schilling had been studying the carburetor problem since before the war, but now it became urgent. She was assigned to work specifically on finding a fix for the Merlin engine's carburetor issues. It was a high-pressure assignment. Rolls-Royce, Britain's premier engine manufacturer, had their best people working on it. Other engineers at Farnborough were investigating various solutions. Everyone understood what was at stake. If they couldn't fix this problem, more pilots would die, and Britain might lose air superiority. The Germans already had superior numbers. Giving them a technical advantage as well could be disastrous. Most engineers approached the problem with complex solutions. Some proposed redesigning the entire carburetor system. Others suggested sophisticated mechanical systems to control fuel flow during negative G maneuvers. Rolls-Royce was working on a pressure carburetor that would solve the problem completely, but that was a major engineering project that would take months, perhaps years, to develop, test, and manufacture. The RAF needed something now, not in 1943. Pilots were dying today, not in some theoretical future. Tilly approached the problem differently. She didn't think about redesigning the entire system. Instead, she focused on understanding exactly what was happening inside the carburetor during negative G flight. She ran test after test, measuring fuel flow at every stage. She calculated the forces acting on the fuel. She observed how the float mechanism responded to sudden changes in G-forces. And slowly, she began to understand the precise nature of the problem. The issue wasn't just that fuel flooded forward during negative G. It was that too much fuel flooded forward too quickly. The carburetor couldn't handle the sudden surge. But what if you could limit that surge? What if you could restrict the fuel flow just enough to prevent flooding, but not so much that you starved the engine during normal operation? You wouldn't need to redesign anything. You would just need to control the flow rate. This was where her practical experience became crucial. Tilly knew that in plumbing and fluid dynamics, you controlled flow rate with a restrictor. This was basic engineering. Put a smaller hole in the line, and less fluid flows through. The question was where to put it, and how small to make it. Too much restriction, and the engine wouldn't get enough fuel during high-power operations like takeoff or climbing. Too little restriction, and it wouldn't solve the negative G problem. She needed to find the exact right balance. Tilly designed a simple metal disc with a carefully calculated hole in the center. It was just a washer, really, made from brass or steel. The hole was precisely sized to allow enough fuel through for normal operations while preventing the excessive surge that caused flooding during negative G flight. The whole thing was less than 2 inches across, weighed almost nothing, and could be manufactured for pennies. It installed in minutes, fitting into the fuel line just before the carburetor's float chamber. No modifications to the engine. No complex mechanisms. Just a washer with a hole in it. Her colleagues were skeptical. The problem had stumped Rolls-Royce's top engineers. The Air Ministry was desperate for a solution. And this woman was proposing that a metal washer would solve it. It seemed too simple, almost insulting. Engineering problems this serious required serious solutions, didn't they? Not something you could make in a machine shop in 10 minutes. But Tilly insisted on testing it. She installed her restrictor in a Merlin engine and began running trials. The test flights were conducted in early 1941, and they would determine whether Beatrice Schilling's simple solution actually worked, or whether months of effort had produced nothing but an expensive washer. The Royal Aircraft Establishment had a flight test section at Farnborough where experimental modifications could be evaluated under controlled conditions. Tilly's restrictor, which was already being called Miss Schilling's orifice by test pilots with a sense of humor, was installed in a Spitfire and prepared for trials. The test pilot assigned to evaluate the modification was understandably cautious. He had experienced the carburetor cutout problem himself in combat, and knew how dangerous it was. Now he was being asked to deliberately put a Spitfire through extreme negative G maneuvers to see if a small metal disc would prevent the engine from dying. If it didn't work, he would be in a powerless aircraft, diving toward the ground, hoping he could recover before impact. This was not a theoretical exercise. Test pilots died regularly doing exactly this kind of work. The first flights were conservative. The pilot took the Spitfire up to altitude, where he would have plenty of room to recover if something went wrong. He started with gentle pushovers, just enough to create slightly negative G-forces. The engine ran smoothly. No coughing, no sputtering, no cutout. He tried steeper pushovers, the kind that would normally cause an immediate engine failure. Still nothing. The Merlin purred along as if it didn't care about gravity at all. The pilot pushed harder, entering steep dives and pulling through into climbs, maneuvers that combined negative G with rapid changes in power requirements. The engine never missed a beat. Back on the ground, the pilot was cautiously optimistic but wanted more testing. These were controlled maneuvers, deliberately planned. Combat was chaos. Could the restrictor handle the violent, unpredictable maneuvers of actual dogfighting? Over the following days, test pilots put the modified Spitfire through increasingly aggressive trials. They simulated combat, throwing the aircraft around the sky with the kind of reckless abandon that combat required. They did split-S maneuvers, diving away from imaginary attackers. They did barrel rolls, snap rolls, and hammerhead turns. They combined negative G dives with full throttle, testing whether the restrictor would starve the engine during high-power negative G flight. In every case, the engine ran flawlessly. The improvement wasn't just about reliability. It fundamentally changed what the aircraft could do. Previously, pilots had to be cautious about negative G maneuvers, rolling or pulling rather than pushing even when pushing would be tactically advantageous. Now they could fly the aircraft through its entire performance envelope without worrying about engine failure. They could push into dives aggressively, chase enemy aircraft down, and maintain full power throughout. In mock combat trials against unmodified aircraft, The difference was dramatic. Pilots with the restrictor installed could pursue targets that would have escaped them before. Tilly Schilling had observed these tests personally, taking notes and measurements. She wanted to understand not just whether the restrictor worked, but how well it worked and whether there were any negative side effects. The data was encouraging. Fuel consumption was essentially unchanged. Maximum power output was unaffected. Takeoff and climb performance remained normal. The restrictor did exactly what it was supposed to do: prevent fuel surge during negative G while having no measurable impact on normal operations. It was an elegant solution, the kind that engineers dream about. One simple component that solved a complex problem without creating new ones. But there was one limitation, and Tilly was careful to document it. The restrictor didn't eliminate the problem entirely. It dramatically reduced fuel surge, but under extreme sustained negative G flight, the engine would still eventually flood. The difference was that instead of cutting out after 1 or 2 seconds, it would now run for 15 or 20 seconds before having problems. For combat purposes, this was more than enough. Dogfights were measured in seconds, and maneuvers rarely sustained negative G for more than a few seconds at a time. A pilot could now chase an enemy aircraft through a dive, maintain full power, and break off or roll before the engine flooded. But for certain specialized maneuvers or prolonged negative G flight, the old limitations still applied. Tilly recommended that the restrictor be considered a field modification, an interim solution that could be implemented immediately while Rolls-Royce continued developing their pressure carburetor for a permanent fix. This was smart engineering and smart politics. She wasn't claiming her washer was a perfect solution for all time. She was offering fighter command a way to save pilots' lives right now, while acknowledging that better solutions would eventually replace it. This made it easier for Rolls-Royce engineers to accept. They weren't being told their work was unnecessary. They were being given an ally in the fight to keep RAF pilots alive. The Royal Aircraft Establishment approved the modification for service use in March 1941. Fighter Command was notified immediately. Instructions were sent to all RAF fighter squadrons explaining the modification and how to install it. Engineering officers were supplied with technical drawings that any competent machinist could use to manufacture the restrictors. The beauty of Tilly's design was its simplicity. You didn't need specialized manufacturing equipment or rare materials. Any machine shop with a lathe and drill could produce restrictors. Many squadrons made their own on-site. Others received pre-manufactured units from central stores. The modification could be installed in under an hour by squadron mechanics. Remove the cowling, disconnect the fuel line, slip the restrictor into place, reconnect the line, replace the cowling. No engine teardown required. No complex adjustments or calibrations. Just install and fly. Within weeks, thousands of Spitfires and Hurricanes were being fitted with Miss Schilling's orifice. Pilots began reporting immediate improvements in combat effectiveness. German pilots noticed that British fighters were no longer breaking off pursuits during dives. The cut-and-run tactic suddenly became much more dangerous for the Luftwaffe. The first combat reports with the modified carburetors began arriving in April 1941, and they told a story of dramatically improved performance. Squadron commanders noted that pilots were engaging more aggressively, pursuing targets they would have previously let go. Kill rates improved. More importantly, survival rates improved. Pilots who might have been shot down while recovering from a carburetor cutout were now maintaining power and fighting their way out of trouble. The psychological impact was enormous. RAF fighter pilots regained confidence in their aircraft. One pilot, Flight Lieutenant Alan Deere, a New Zealand ace flying Spitfires, later wrote about the difference the modification made. Before the restrictor, he had lost several kills because his engine cut out during aggressive pursuit. He had also nearly been killed twice when the cutout left him vulnerable at critical moments. After the modification was installed, he described feeling like he was flying a completely different aircraft. He could dogfight the way he had been trained, using the full performance envelope of the Spitfire without self-imposed limitations. In his estimation, the modification improved combat effectiveness by at least 25%, possibly more. Fighter Command's Operational Research Section attempted to quantify the impact. This was difficult because so many variables affected combat outcomes: pilot experience, tactical situation, numerical odds, weather conditions, and countless others. But by comparing engagement reports before and after the modification, patterns emerged. Aircraft with the restrictor installed were statistically more likely to score kills and less likely to be shot down in turning fights and dogfights involving rapid altitude changes. The numbers weren't perfect, but they suggested that Tilley's simple washer was saving lives and winning engagements. The modification's timing was particularly fortunate. In 1941, the RAF was transitioning from defensive operations over Britain to offensive sweeps over occupied France. These operations, called rhubarbs and circuses, involved escorting bombers and conducting fighter sweeps deep into enemy territory. Combat occurred over hostile ground, where any mechanical failure could result in capture or death. The carburetor modification gave RAF pilots the confidence to engage aggressively even over enemy territory, knowing their engines wouldn't fail them at critical moments. German pilots noticed the change. Luftwaffe combat reports from mid-1941 onward note that British fighters were becoming more aggressive in the dive, no longer breaking off pursuits as predictably. The cut-and-run tactic, which had been reliable for months, became much less effective. German pilots had to fight more defensively, which played to the Spitfire's strengths. The Bf-109 was slightly faster in level flight and could dive away, but the Spitfire turned better. If German pilots couldn't escape by diving, they had to turn and fight, where the Spitfire had the advantage. This shift in tactical dynamics affected loss rates on both sides. The modification remained in service until late 1943. When Rolls-Royce finally completed development of their pressure carburetor. This was a complete redesign that used fuel pressure rather than gravity to feed the engine, similar to the German fuel injection system but using British engineering principles. The pressure carburetor eliminated the negative G problem entirely, and improved engine performance in other ways as well. But it took 2.5 years to develop, test, and manufacture in sufficient quantities. During those crucial years, Tilly-Schilling's restrictor was the only thing preventing carburetor cutouts. Historians and military analysts have attempted to calculate how many pilots' lives were saved by this modification. The numbers are necessarily speculative, but estimates range from several hundred to over 2,000. The calculation considers how many engagements were won that would have been lost, how many pilots avoided being shot down during carburetor cutouts, and how many kills were achieved against enemy aircraft that would have escaped. Even the conservative estimates suggest that Tilley's modification saved hundreds of lives and destroyed hundreds of enemy aircraft that would otherwise have survived. The financial impact was equally remarkable. The restrictor cost approximately 50 cents to manufacture, depending on materials and production methods. Installing it took less than an hour of mechanic time. No special tools or equipment were required. In contrast, redesigning the entire carburetor system cost Rolls-Royce hundreds of thousands of pounds and required retooling manufacturing facilities. Developing a completely new pressure carburetor system cost even more. Tilley's solution delivered immediate results for essentially zero cost. In terms of return on investment, it may be one of the most cost-effective military modifications in history. Fighter Command officially credited the modification with significantly improving combat effectiveness during the critical 1941 to 1943 period. This was when the RAF was rebuilding after the Battle of Britain, training new pilots in large numbers, and beginning offensive operations over Europe. Maintaining air superiority during this period was essential for Britain's survival and eventual victory. The carburetor restrictor played a small but meaningful role in that success. It didn't win the war by itself, obviously, but it helped keep British pilots alive and fighting effectively during years when every advantage mattered. Despite the dramatic impact of her modification, Beatrice Schilling received relatively little public recognition during the war. This was partly due to wartime secrecy. The British government didn't want to publicize technical modifications to military aircraft, as that information could be useful to the enemy. But it was also due to the era's attitudes toward women in technical roles. Male engineers were routinely credited for their contributions and received awards and recognition. Women, even those doing identical or superior work, were often overlooked or their contributions minimized. Within the engineering community and among RAF pilots, however, Tilly was well known and deeply respected. Pilots who flew with her modification installed knew they owed her their lives, sometimes quite literally. The nickname, Miss Schilling's Orifice, was used with affection and gratitude, though its double meaning wasn't lost on anyone. It was a way for pilots, with their dark sense of humor, to acknowledge both the modification and the woman who created it. Some squadrons painted small washers on their aircraft as an unofficial tribute. The Royal Aircraft Establishment recognized her contribution with promotions and additional responsibilities. By the end of the war, she had risen to a senior technical position, supervising other engineers and leading major research projects. This was extraordinary for a woman in that era. Most female engineers, even highly qualified ones, were restricted to junior positions and routine work. That Tilly was given significant responsibility and authority speaks to how exceptional her abilities were and how much respect she had earned from her colleagues. In 1948, 3 years after the war ended, Beatrice Schilling was awarded the Order of the British Empire for her contributions to aircraft engine development. The citation mentioned her work on carburetors but didn't specifically describe the restrictor modification. By that time, with the war over and the pressure carburetor in service, the wartime modification was already being forgotten by the public. But to those who understood what she had accomplished, the award was long overdue recognition of work that had saved countless lives. Tilly continued working as an engineer for decades after the war. She specialized in engine development, and became an expert in motorcycle and automobile racing engines. She continued racing motorcycles herself, competing into her 50s and setting speed records. She married another engineer, George Naylor, in 1938, and they worked together on various projects throughout their lives. Unlike many women of her era who were expected to give up careers after marriage, Tilly never stopped working in her field. She was an engineer until she retired, and in many ways, she remained an engineer until she died in 1990 at age 81. Her legacy extends beyond the specific technical contribution of the carburetor restrictor. Beatrice Schilling was a pioneer who demonstrated that women could excel in fields that society insisted were male domains. She did this not through advocacy or argument, though she certainly faced and overcame discrimination, but through the quality of her work. She solved problems that others couldn't solve. She designed elegant solutions to complex challenges. She saved lives through her intelligence and skill. In doing so, she opened doors for generations of women engineers who followed. The carburetor restrictor itself is now a small footnote in aviation history. Most books about the Battle of Britain and the air war over Europe mention it briefly, if at all. The pressure carburetor that eventually replaced it is considered the real solution, and Rolls-Royce engineers receive most of the credit for solving the negative G problem. This is somewhat unfair but understandable. The pressure carburetor was indeed a better long-term solution, and developing it required years of sophisticated engineering work. But that doesn't diminish what Tilly accomplished with her simple metal washer. Modern engineers studying the carburetor restrictor often express admiration for its elegance. In an age of complex systems and sophisticated solutions, there's something beautiful about solving a critical problem with a 50-cent part that anyone can manufacture and install. It's a reminder that engineering isn't always about complexity or advanced technology. Sometimes the best solution is the simplest one, the one that solves the immediate problem efficiently and effectively without creating new complications. Tilley's restrictor exemplifies this principle. Several aviation museums in Britain now display examples of Miss Schilling's orifice alongside Spitfires and Hurricanes. The Imperial War Museum includes it in exhibits about technological developments during the Second World War. Engineering societies use it as a teaching example of elegant problem-solving and the importance of practical testing alongside theoretical analysis. In the motorcycle racing community, where Tilley was well known and respected, she is remembered as a pioneer and champion who happened to also save thousands of lives during the war. Perhaps the greatest tribute to Beatrice Schilling is that pilots who flew with her modification installed trusted it completely. In combat, trust in your equipment is everything. If you can't trust your aircraft, you hesitate, you second-guess yourself, and you die. The carburetor restrictor gave pilots back their confidence in the Spitfire and Hurricane. They knew that when they pushed into a dive, their engine would keep running. They knew they could fly aggressively and fight to their limits without the aircraft betraying them. That trust, that confidence, was Tilley Schilling's real gift to the RAF. The washer was just the mechanism that delivered it. To fully appreciate Beatrice Schilling's achievement, we need to understand the broader context of women's contributions to engineering and the war effort during the Second World War. Tilley was not the only woman doing technical work during this period, though she was certainly among the most accomplished. The war created opportunities for women in fields that had been virtually closed to them before, though these opportunities came with significant limitations and often disappeared once peace returned. In Britain, women worked in munitions factories, aircraft assembly plants, and research facilities. They operated machinery, performed quality control, and contributed to production in countless ways. Some, like Tilley, held positions of genuine technical responsibility. More commonly, they were assigned to repetitive tasks under male supervision. The wartime propaganda praised women workers, but it also made clear that these were temporary arrangements. Once the men came home from war, women would be expected to return to domestic roles. The engineering profession was particularly resistant to women. Unlike nursing or teaching, where women had established a foothold by the 1940s, engineering remained almost entirely male. Universities that accepted female engineering students often did so reluctantly, and in small numbers. Professional engineering societies either excluded women entirely or relegated them to auxiliary status. Employers assumed women couldn't handle the mathematical demands, the physical requirements, or the decision-making responsibilities of engineering work. What made Beatrice Schilling exceptional was not just her technical ability, though that was certainly remarkable, but her persistence in the face of constant discouragement. From childhood through university and into her professional career, she encountered people who told her, directly or indirectly, that she didn't belong in engineering. Some were openly hostile. Others were patronizing, treating her as a curiosity or novelty. Very few took her seriously based on her qualifications alone. She had to prove herself repeatedly, earning respect through achievement rather than receiving it as a professional courtesy. The carburetor restrictor episode illustrates this perfectly. When Tilley proposed her solution, many of her male colleagues were skeptical not because the design was flawed, but because they couldn't believe something so important could come from a woman. The problem had stumped Rolls-Royce's best engineers, all men. How could this woman solve it with a simple washer? The skepticism wasn't rational or based on engineering principles. It was prejudice, pure and simple. Only when test flights proved the modification worked did attitudes begin to change. Even then, recognition came slowly and incompletely. Male engineers who contributed to wartime aircraft development received public acclaim, honors, and post-war career opportunities. Tilley received respect within a narrow professional circle but remained largely unknown to the public. This pattern was typical. Women's contributions during the war were often minimized or forgotten once peace returned. The narrative of the war emphasized male heroism, male sacrifice, and male technical achievement. Women were supporting players at best. This erasure had real consequences for post-war opportunities. Women who had worked as engineers, scientists, or in other technical roles during the war often found themselves pushed out afterward. Companies that had eagerly employed women when men were unavailable suddenly discovered they preferred male employees when veterans returned. Professional societies that had tolerated women during the emergency reverted to excluding them. Universities that had accepted female students reduced admissions. The progress women had made was not just stalled but actively reversed. Beatrice Schilling was fortunate in some respects. Her wartime achievements and the respect she had earned at the Royal Aircraft Establishment protected her position. She continued working in her field throughout her career, advancing to senior positions and leading important projects. But she remained an exception. Most women engineers of her generation either left the profession or were forced into supporting roles. The doors that the war had seemed to open for women in engineering largely closed again in the 1950s. It would take decades for those doors to reopen. The feminist movement of the 1960s and 1970s challenged barriers in many professions, including engineering. Legal protections against discrimination made it harder for universities and employers to exclude women overtly. Cultural attitudes slowly shifted. By the 1980s and 1990s, women in engineering were no longer quite as rare as in Tilley's day. But even today, engineering remains a male-dominated field where women face obstacles that male colleagues don't encounter. Beatrice Schilling's legacy includes her role as a pioneer who demonstrated what women could achieve in engineering despite institutional barriers. She didn't do this alone or as part of an organized movement. She simply refused to accept that her gender disqualified her from pursuing work she loved and excelled at. By succeeding on her own terms, she helped pave the way for others. Every woman engineer today benefits, directly or indirectly, from the paths pioneered by women like Tilley who refused to be excluded. The carburetor restrictor story also raises interesting questions about how history remembers technical achievements. Why do some innovations become famous while others fade into obscurity? The Spitfire itself is iconic, one of the most recognizable aircraft in history. The Merlin engine is celebrated as a masterpiece. But the simple modification that made them more effective in combat is barely remembered. This isn't entirely surprising. Dramatic innovations capture imagination more than incremental improvements. But it does mean that important contributions are often overlooked. Part of the explanation may be that Tilley's solution was too simple. Engineering narratives tend to celebrate complexity and sophistication. A pressure carburetor that required years of development and sophisticated manufacturing feels more impressive than a washer you can make in minutes. But effectiveness matters more than complexity, and by that measure, Tilley's restrictor was extraordinarily successful. It solved an urgent problem immediately and saved lives while more sophisticated solutions were developed. That deserves to be remembered. The story of Beatrice Schilling and her 50-cent metal washer is, on its surface, a story about engineering. It's about identifying a problem, understanding its root causes, and developing an elegant solution. But it's also about much more than that. It's a story about persistence in the face of discrimination, about having the confidence to trust your own analysis even when others are skeptical, and about the sometimes surprising ways that individuals can affect history. When Tilley Schilling looked at the carburetor cutout problem, she saw something that the teams of male engineers at Rolls-Royce and the Royal Aircraft Establishment had missed. This wasn't because she was smarter than them, though she was certainly brilliant. It was because she approached the problem differently. While they were thinking about comprehensive redesigns and sophisticated mechanisms, she was thinking about the immediate practical problem. How do you stop fuel from surging forward during negative G flight? You restrict the flow. It was almost embarrassingly simple once someone thought of it. The modification saved an estimated 2,100 pilots' lives, though the real number could be higher or lower. Every one of those pilots was someone's son, husband, brother, or friend. Many of them went on to fight through the rest of the war. Some survived and lived long lives after the war ended. Their children and grandchildren exist because Beatrice Schilling understood fluid dynamics and had the practical sense to design a simple restrictor. When we talk about how individuals affect history, we usually think of generals, politicians, or inventors of major technologies. But sometimes history turns on something as small as a metal washer designed by a woman on a motorcycle. The RAF recognized at the time that Miss Schilling's orifice was a game-changer, though wartime secrecy prevented public celebration of it. Fighter Command knew they had been given back a critical capability. Pilots knew they could trust their aircraft again. Squadron commanders knew their men had a better chance of surviving each mission. The modification didn't win the war by itself. The Battle of Britain had already been won before it was implemented. But it helped Britain maintain and extend air superiority during the crucial years when the outcome of the war was still very much in doubt. What makes Tilly's achievement particularly remarkable is that she did it while facing constant discrimination and skepticism. A male engineer proposing the same solution would have been taken seriously immediately, tested promptly, and credited appropriately. Tilly had to overcome doubts about her competence that had nothing to do with her qualifications or her proposal. She had to prove herself again and again, not because her work was deficient but because she was a woman doing work that society insisted women couldn't or shouldn't do. That she succeeded despite these obstacles speaks to extraordinary determination and confidence. The story also reminds us that effective solutions aren't always complex ones. In our modern age of sophisticated technology, we sometimes forget that simple approaches can be powerful. Tilly's restrictor didn't involve advanced materials, complex mechanisms, or sophisticated electronics. It was a piece of metal with a hole in it, carefully sized and positioned. But it worked, and it worked immediately, and it could be manufactured and installed anywhere with minimal resources. Sometimes that's exactly what's needed. Today, Beatrice Schilling is slowly receiving the recognition she deserves. Aviation historians have rediscovered her story. Engineering educators use her work as an example of elegant problem-solving. Feminist historians cite her as a pioneer who broke barriers in a male-dominated field. Museums display her modification alongside the aircraft it helped save. But she remains less famous than she should be, her name less well known than many men who contributed less to the war effort. This is partly historical accident. The carburetor cutout problem was secret during the war and didn't capture public imagination afterward the way major technologies like radar did. Tilly herself was modest and didn't seek publicity. After the war, she continued working quietly in her field, developing engines and racing motorcycles, but not promoting her wartime achievements. She was content to have solved the problem and saved lives. The fame and recognition that others sought didn't interest her much. But it's also partly the result of systematic bias in how history remembers technical achievements. Men's contributions are documented, celebrated, and taught to future generations. Women's contributions are often overlooked, forgotten, or attributed to others. This wasn't unique to Tilly or to engineering. It happened across fields and countries. The deliberate recovery and recognition of women's historical contributions is important work that continues today, correcting the incomplete historical record. For RAF pilots who flew with Miss Schilling's orifice installed, none of this mattered. They didn't care whether the solution came from a man or a woman, whether it was simple or complex, whether it was properly recognized or not. They cared that it worked, that they could dive after enemy aircraft without their engines cutting out, that they had a better chance of survival. In that sense, Tilly achieved exactly what she set out to do. She solved a problem that was killing pilots, and she did it quickly and effectively. The rest was just noise. The metal washer itself, that 50-cent piece of brass or steel, represents something important about engineering and about problem-solving more generally. The best solution isn't always the most obvious one or the most complex one. It's the one that works, that solves the immediate problem effectively while being practical to implement. Tilley's restrictor exemplified these principles. It addressed the exact problem without trying to be more than it needed to be. It was manufacturable, installable, and effective. Those three qualities, more than sophistication or elegance, define successful engineering. In the decades since the war, aircraft engines have become vastly more sophisticated. Modern fighters use computer-controlled fuel injection systems that can adjust mixture and flow thousands of times per second, adapting to altitude, temperature, airspeed, and g-forces automatically. The carburetor itself is obsolete technology, replaced entirely by electronic fuel management. In this context, Ms. Schilling's orifice might seem like a quaint historical curiosity, a primitive solution to a problem that no longer exists. But the principles behind it remain relevant. Engineers still face problems that require immediate solutions while more comprehensive fixes are developed. They still have to balance sophistication against practicality, ideal solutions against achievable ones. They still need to understand not just how systems are supposed to work theoretically, but how they actually behave under real-world conditions. These lessons that Tilly Schilling exemplified are timeless. They apply whether you're working on aircraft carburetors in 1941 or designing software systems in 2025. Beatrice Schilling died in 1990, at the age of 81. By then, she had lived long enough to see women's opportunities in engineering expand dramatically compared to when she started. She had witnessed the transition from piston engines to jets and then to computer-controlled systems. She had seen her field transformed multiple times over. But she had also seen that the fundamental challenges of engineering, understanding problems deeply and designing effective solutions, remained constant across technologies and eras. The pilots she saved never forgot her, those who knew the story. In veteran gatherings and squadron reunions, old men who had flown Spitfires would sometimes mention Miss Schilling's orifice, usually with a smile, sometimes with visible emotion. They were alive because a woman they had never met understood carburetors better than anyone else in Britain. Some of them made efforts to meet her after the war, to thank her personally. She was always gracious but never sought the spotlight. She had been doing her job, solving problems, saving lives. That was enough for her. The story of how one woman's 50-cent metal washer made Spitfires outfly every Bf 109 and saved thousands of pilots is ultimately a human story. It's about intelligence and determination. It's about seeing solutions that others miss. It's about having the confidence to propose simple answers to complex problems. It's about persistence in the face of discrimination and doubt. And it's about the profound impact that one person, working diligently at what they do best, can have on history. Beatrice Schilling was that person, and her legacy endures not just in history books, but in every pilot who survived because she understood fuel flow and had the courage to install a washer in the right place.